Welcome back, everybody. Today we are finally going to discuss the converse modularity in a little bit more detail than we were able to do when we were outlining a sketch of the proof of Fermat's last theorem. Let's recall the statement. Let's let F be a weight 2 new form for gamma 0 n with rational coefficients a sub n. Then the statement is there's a unique up to q isogeny elliptic curve E over Q, or E sub F over Q if you like, with conductor n matching this level here, such that F sub E equals F, where F sub E is the sum from n equals 1 to infinity of a sub n of E Q to the n, where the a sub n of e's, remember, are managing solution counts to the reductions of E mod P for various primes P. For example, a sub P of E, you might recall, is P plus 1 minus the number of FP points on the reduction of E mod P. Okay, so proof. I'm just going to give a sketch. I'm going to combine essentially some stuff from Diamond and Sherman chapters 8 and 9 and Milne's elliptic curves chapter 5. Let's let F be our new form. And what I'm going to do is this elliptic curve here, E over Q, is going to end up being the abelian variety attached to F that we defined last time, which we know is an elliptic curve because F has rational coefficients. That was all covered last video. So I'm going to set E or EF equal to that elliptic curve attached to F from last video. And again, I'll just call it E. Okay, what we have to do is show that EF and F have the same L function. That's really what's going on here. Let's assume initially that x0n has genus 1. If you go back and look at the proof of the construction of E sub F, or of A sub F more generally, the abelian variety attached to F, you see that it's in essence the largest quotient of the Jacobian J0 of n on which the Hecke operators T sub n and the coefficients A sub n agree. Remember, it was Jacobian mod annihilator ideal. Okay, so in particular, if I compose that quotient map J0 of n to AF, or EF in this case, with the natural map that any curve has to its Jacobian, so we have a map x0n to J0n here, this gives me a Q isogeny from x0n to EF. No problem, right? Now, technically, you have to make sure we know this is defined over Q. We already talked about that. What you don't necessarily know is that this quotient map is defined over Q, but it is, and you can check that relatively easily. Okay, and so what's going on here is I just have a Q isogeny x0n to EF already if x0n has genus 1 initially. Well, the conclusion that I'm looking at up here is Q isogeny invariant. And so I can, without loss of generality, just assume EF is x0n, you see. Okay, so now let's let P be a prime that doesn't divide n. It turns out EF has good reduction at P. We discussed that last video. And it also turns out that for any prime L that isn't P, the reduction map from the L-adic Tate module of E to the L-adic Tate module of the reduction of E is an isomorphism. So this is the reduction of E mod P. Okay, a good reference for this is Math Stack Exchange reductions of isogynous elliptic curves, if you want to see why this is true. All right, so essentially what's going on here is this is all Eichler-Shimura. By Eichler-Shimura, when I'm working on this reduced curve E tilde mod P, the Hecke operator T sub P is just Frobenius plus Verschiebung. Verschiebung is just the transpose of Frobenius, you recall. Okay, so I have a whole video on Eichler-Shimura if you want to go back and watch that. And so what I'll do is I'll just take traces of both sides on the L-adic Tate module of the reduced curve. Okay, and remember, E tilde here is just the reduction of x0n mod P. Okay, so what do I get when I do that? You can show using a pretty easy characteristic polynomial argument that the trace of Frobenius is just APE, okay? Or I guess using my notation above, AP of E. And then you can also prove that whatever the trace of Frobenius is, trace of Verschiebung, its transpose, must be the same. And that's just an easy degree argument because Verschiebung is produced by the theory of dual isogenies. So it's easy to see these are both the same, whatever they are. And that trace of Frobenius is the kind of the pth coefficient in this sum here. Okay, so the question is what's going on the left-hand side? Well, that's pretty easy, right? So what's the trace of TP? Well, you know the eigenvalues of TP as an operator. Like when you plug F into it, you know the eigenvalues are going to be AP and AP bar essentially, right? Okay, well, the trace is the sum of the eigenvalues, and all of my coefficients are rational here, so all of them are real. And so the eigenvalues, the trace will be the sum of the eigenvalues, which is AP plus AP bar, but that's just 2AP, right? And so I get 2AP equals 2APE. Well, then AP is APE. Now, this only holds for almost all primes P, all the primes P not dividing n. That it holds for all P, and that the conductors here actually match in the statement to the converse of modularity, that all follows from Carriol's hard theorem, which I haven't talked about in a while, but that's very hard work. So we can, without Carriol, we can get just about the converse to modularity. Not quite though. We can get that the L functions of these two guys match for almost all primes, and we can't necessarily verify that their conductors match. Okay, so this was all under the assumption that x0 of n had genus 1 initially, but the point is that's kind of generically how the argument goes. The general case is similar, but at various places in the arguments, you replace the elliptic curve E sub f by a different curve, the abelian variety attached to f or whatever, or the Jacobian of a different curve or quotients of it, various things like that. But the general structure of the argument works exactly like I've shown you here. All right. So thanks for watching, and I'll see you all next video.